3, 2, 1. Hi everybody, this is Austin Hoggett here to give you another lecture from OpenStack's Intermediate Algebra. Today we're going to start in Chapter 6 on factoring trinomials. And you can see that there's two learning objectives and basically two different forms that these questions could be asked in. But the generalized expression is the one I want you to draw your attention to. Today we're going to learn something called the AC method. The AC method is named after the coefficients that you see from this generalized form for a trinomial. The ax squared plus bx plus c form is one that you often see when learning about how to solve more complicated equations. And that's ultimately where factoring is most useful, and is learning how to solve different types of equations. So whereas before we might have had a single variable with one unknown value and asked to solve for it using the properties of equality, now we have something a little bit more difficult to contend with, more something like 3x squared plus 1x is equal to 2 or something like this. And so we cannot just use the properties of equality like we did before to be able to solve this. We use a factoring method, and we'll find that there's actually other ways as well to solve these more complicated types of problems. But at the root of all of this is learning how to factor. So let's start with this particular method. We're going to look at really the easier of the two formats, but recognize that these are really the same type of question. What the difference has to do with is whether or not the coefficient on my first term, this a value, is either equal to 1 or it's not equal to 1. So we would maybe say that the version where this is equal to 1 is the quote easy version, and this is the quote hard version. The difficulty level has to do really with the number of steps involved. When a is equal to 1, all we have to identify are two questions. Let's look at those together. Generally speaking, the form x squared plus bx plus c will have some factor that looks like a pair of binomials. So take a look at the example on the left. X squared plus 5x plus 6 factors to give me x plus 2 times x plus 3. We learned in the last chapter how to actually find the product of binomials to confirm that this actually does produce the trinomials you see. So for now, take the assumption that any trinomial in this form actually does factor to give me x plus or minus some number times x plus or minus some other number. You can see my generalization here, x plus m times x plus n. Let's actually work out what the criteria are to identify what the factors would be. If I multiply these through using the FOIL method, in other words, take the first, the outer, inner, and last terms and multiply them together, we should be able to get what would be a generalized expression for our trinomial. So in the case where I multiply x times x, I get x squared. Our two inner terms and outer terms are going to be coefficients like n times x plus m times x. And the last two terms multiply together to give me some numeric value m times n. In other words, the two middle terms here, nx and mx, actually should add together. So b times x should be the same as nx plus mx. The constant at the end should be equal to whatever m times n should be. With this linkage in mind, we can actually work backwards to figure out what the original factors of any of these types of trinomials should be. We're not always guaranteed that this method works because it's limited in instances where this value for b and x are going to be integers. But in most cases, we'll see that it's quite effective. So let's try an example or two. Before we do, let's recap. Given any kind of expression in this form, x squared plus bx plus c, which is again the quote easy version, where a is equal to 1, we identify the answer to two questions. What are the two values that multiply together to give me c that also add together to give me b? Technically speaking, we should actually say that they need to multiply together to give me a times c. And in reality, because the a term here is equal to 1, it really just works out to being C. But this is what we'll be using in the quote hard version of this question, where A is actually not equal to 1. So if we can find an answer to what are the values of m and n, we go directly from our original trinomial to the factored version, which is great. And again, we can actually use the FOIL method to confirm that we've actually got the correct values. So let's take a look at this example together. I've got x squared plus 11x plus 24. My b value, the middle coefficient, is 11. The c value is 24. So my task is to find m times n that multiply together to give me that constant at the end, that also add together to give me the middle coefficient. So what are those values, and how do I find them? A good way to approach this is actually to think about one question at a time. The first of which is probably easier, the product. What two values multiply to give me 24? Well, it's a pretty short list. What are all the values that multiply to give me 24? 1 times 24 is maybe the easier of all of them. We could also say, well, 2 times 14 would work. Or excuse me, 2 times 12. And then we have 3 times 8 and 4 times 6. So a lot of times I will just start with 1 times whatever the number is, which is usually not the correct answer, but it at least gives me a starting point. Listing out all the factors in this way, I can think about my divisibility rules to generate that list. But the purpose is to not try to conjure up an answer to both of these questions simultaneously, but to answer one at a time. So those are all the candidates for the answer to what are the values m and n. What of these candidates answers the second question? Which adds to give me 11? Well, there's only one pair, 3 plus 8. And so that gives me the solution. Now, which value is actually supposed to be which? In this case, it doesn't quite matter. I can set m to be either 3 or 8, or n to be either 3 or 8. But now that we have an answer to those questions, we ought to be able to go and put the factored version here together. So because this is the quote easy version, where the coefficient on my square term is equal to 1, this factors to give me x plus m times x plus n. So we get a solution here of x plus 8 times x plus 3. So again, by the FOIL method, I could come back and actually ensure that this is correct. But let's move on to another example. In this case, I have a similar scenario. My coefficient on the square term is equal to 1. My middle coefficient now is actually negative 11, and the constant at the end is 28. What changes here is really thinking about how the signs for the values of m and n should work. In this case, I'm still interested in identifying the values of c, or rather the values of m and n that multiply to give me c. But take a look at this slide here. When c is negative, it tells me that m and n have opposite signs. When c is positive, m and n have the same sign. How does that affect our problem here? Take a look again at the middle coefficient. It's negative. So to add two numbers together to get negative 11, it would seem that they either both need to be negative, or thinking about it another way, if two values multiply together to give me a positive number, but then add together to give me a negative number, one of the signs on those factors has to be different. So in this case, again, we're still trying to identify one step at a time what the answer to each of these two questions are. And just like before, I'll start with the first, which is easier. How do I get a bunch of things to multiply together to give me negative 11, right? So looking at the expression here, 28, I could factor it into 1 times 28, 2 times 14, and 4 times 7. And I think that's the only factors. So for our purposes here, I've got to, again, think about what are all these sort of signs supposed to be for each of these expressions. If I'm going to add two numbers together to get negative 11, it looks like none of these would work unless I make them negative. For instance, 4 plus 7 would give me positive 11 and still multiply to give me 28. But if I make them both negative, Suddenly it works for both of my equations. Those are the two values that I will then use for m and n. So I get a final answer here of, when this factors, of y minus 4 times y minus 7 for the solution. So we have to pay attention to our signs when looking at the two questions posed using the AC method. Again, to kind of think about this more broadly, given an expression x squared plus bx plus c, we ask two questions. What are the factors of c that add up to b? And depending on whether or not that constant at the end is positive or negative could change how we think about the signs of those factors. Are they going to be the same, or are they going to be opposites? So keep that in mind. Now let's look at the harder version of this type of question. The AC method, again, comes from these generalized expressions. Now, what we'll end up with are two of the same exact questions. Find values that multiply together to give me not c, but a times c, that also add together to give me the middle coefficient b. Let's take a look at the example here and see what the additional step to solving would be. The AC method starts with asking if we can identify any greatest common factors. We didn't really think about this last time, but that's mostly because our square term had a coefficient of 1. Therefore, none of the other terms have a GCF with it. But if we make a some value other than 1, it's possible that we can remove a GCF from all three of our terms. Step 2 is to then pose the two questions we've seen already. What are the values that multiply together to give me AC and add together to give me B? What we do next is not going directly to the factored version, but to actually split the middle term into two parts. We saw a version of this earlier when we demonstrated how factoring of a general expression into the form x plus m and x plus n gives me some middle expressions that add together. Here we have to factor by grouping to actually finish the problem. And of course, as usual, we can actually multiply things back together at the end to confirm that we really do get back the trinomial we started with. So let's try a specific example. Here I've got 6b squared minus 13b plus 5. And again, my task is to find values that multiply together to give me a times c. In this case, I get 6 times 5 is 30. And I also need to identify those same values that would add to give me my middle coefficient, negative 13. So just as before, I might start with, what are all the different ways that I can multiply two numbers together to get 30? We would say maybe 1 times 30, 2 times 15. We could also have 3 times 10, 5 times 6, and I think that's the end of my list. Looking at this, again, none of these add up to give me negative 13 unless I give them all negative signs. If two numbers are negative and they multiply together to give me a positive, then I can find that negative 3 and negative 10 would answer my two questions. So those are the values of m and n. Now comes the next part. Instead of going directly to the solution, we take our original trinomial here and we split it up into two parts. We're going to take the middle bit and split it into two pieces, 3 and 10. So this now becomes 6b squared minus 3b minus 10b plus 5. To factor by grouping, we look at the first two expressions and the last two expressions and identify the GCF. 6b squared and negative 3b. Look at their coefficients. They both have at least a 3 in common, and they both have at least a b in common. If I were to take and divide each of those terms by the 3b that I've removed, we ought to get an undistribution of that expression. 6b squared divided by 3b would give me something like 2b, and then negative 3b divided by 3b would give me minus 1. Remember that when factoring by grouping, we should expect the exact same binomial, 2b minus 1, to show up in the second pair. Notice that the signs for my second pair of terms, negative 10b plus 5 are opposite of the signs of the first two terms. Looking at that second pair, I should actually remove a negative 5 as my GCF. For instance, if we take negative 10b and divide by negative 5, we now end up with the positive 2b we should expect if we want our binomials to match. And again, positive 5 divided by negative 5 gives me negative 1. My binomials match, and I'm sure that the factor by grouping can continue. So now that we know that the new common binomial is 2b minus 1, we remove it, and what we're left with is the product of the remaining factors, 3b minus 5. While this looks strange, it does multiply back together to give me the original expression. So that's the AC method in the, quote, hard version. Again, the additional step required is to take our middle coefficient here and split it into two parts so that we can factor by grouping. Let's look at one or two more examples. Here again we have the AC method, our A value 6, B value 7, C value 2. We're tasked with finding the product of two numbers that multiply together to give me 12, that also add together to give me 7. Looking at the factors of 12, and there's not that many, 1 times 12, 2 times 6, 3 times 4, hopefully it's obvious that this pair here is what we need. Jotting that down, we get m is equal to 3, n is equal to 4. So again, the next piece of the puzzle is to just split our middle term into two pieces. We will now express this as 6x squared plus 3x plus 4x plus 2. With that, we can take out the GCF of the first pair and then the second pair. In this expression here, with my first two pair terms, they have a common expression of 3x. If I remove that, I'm left with x plus 1. I should expect the same for the second pair. So looking at my other pair of factors or terms, 4x plus 2, they also have a common factor of just 2. Once removed, leaving me with, again, x plus 1. My new GCF is this binomial. So if I remove it, I finally get my solution here of x plus 1 times the product 3x plus 2. Here is my final solution to the factors of that original trinomial. So one last example I'll show is an instance where perhaps we have to remove a GCF first before we can continue with this particular method. So let's look at that last example. Notice in this case, I've got 16x squared negative 32x plus 12. And if I started this problem off just by identifying the values for A, B, and C, it would be kind of a pain, mostly because the numbers are quite large. And so that indicates to me that there could be some simplicity from removing a common factor. For instance, between 16, 12, and 32, we could say that 4 is the GCF. If I divide everything by 4, in essence, we could remove a common factor. So 4 would give me an expression here of 4x squared minus 8x plus 3. And this is the trinomial that we actually want to factor. Okay. So now our A terms are different. We come back and erase. My dog is very turned up about something. We get as our coefficients positive 4, negative 8, and positive 3. So now we're looking for factors that multiply together to give me 12 and add together to give me negative 8. And so the question here changes in difficulty just due to the fact that I don't quite have as large of values to worry about. So thinking again about what are the different factors of 12 that would add up to be negative, I have to think about it by understanding again that the two values are going to end up being with the same sign, so that they'll multiply to be positive but add to be negative. In this case, the two factors I'm interested in are going to be n equals -2, m equals -6. The product gives me that +12, and the sum gives me -8. Since this is again the quote hard version of the AC method, we'll take what's inside the parenthetical here and split that middle term so that we can factor by grouping. So just focusing on what's inside the parenthetical, I end up with something like 4x squared minus 2x minus 6x plus 3. Now we can factor by grouping just as before. Looking at the first pair of terms, 2x is my greatest common factor. If I remove it, I'm left with x minus 1. Looking at my second pair, I have to be careful again about the signs when I choose my GCF. I want to remove actually a -3 as the greatest common factor. When I go to do the division, -6x divided by -3 gives me a positive x. +3 divided by -3 gives me the -1 that I need to finish the problem. Again, my binomials now match, and so I can remove that binomial x minus 1 and multiply it by the sum of the remaining factors, 2x minus 3. Here, finally, is my solution to this last problem. Now, one thing I did forget is the 4 that we started with. Technically speaking, it's still part of the factors. So I should come back in here and actually add that in. So often you'll find that these little numeric values that are still left over can be easy to forget about. Certainly, I just did. So be cautious of cases where the numeric values for your AC method are quite large. It indicates that you could probably identify a GCF to remove to make this a lot easier. So I hope that you remember the steps here. Again, the criteria that you see down here is what's most critical. Finding those values that multiply to give me AC, but also add together to give me the middle coefficient. So take a look at your homework, try some practice problems from the notebook, see what you can do to master this particular technique. It shows up, again, I promise you, in lots of different areas. So see what you can learn from this particular lecture. We'll see you next time.